Hi, I'm Aidan from the Collins Hill branch of the Gwinnett County Public Library System. Welcome to Codemaking and Codebreaking, a series of programs in which we look at codes and ciphers, explain how they work and how you can crack them. In this episode, we will be discussing transposition ciphers and looking at two examples, the rail fence and the columnar transposition ciphers. But first we need to define our terms. What is a transposition cipher, and how does it differ from the substitution ciphers that we've looked at in the past? In a substitution cipher, we take a letter and we change the way it's represented, but it stays where it is in the document. In a transposition cipher, we take that item, that letter or number, and we move it to another position within the document, and we do that using some sort of mathematical formula. Let's take a look at how this works with an example. The rail fence cipher. With the rail fence cipher, we write our words out in a zigzag formation. Once we've completed writing our words out that way, we then read line by line from left to right. Let's take a look at an example. My secret message will be, can we have pizza tonight? I will be using 3 lines or rails. My completed grid looks like this. Now I need to write out my ciphertext that I will send to the person who will receive my message. Now, note that there is no punctuation in the message, and I've blocked it into sets of 5 letters. This helps prevent any third party from decoding it because they can't use that punctuation as a guide for where the word should be. So as you can see, it is pretty simple to encode a message using the rail fence cipher method. The question is, how simple is it to decode it when you receive it? Well, your recipient is going to need a piece of information from you. They need to know how many rails you used. Now, the reason they need this information is they need to work out the cycle length. Now, a cycle is the amount of spaces between the first letter that appears on the top rail and the second letter that appears on the top rail. For example, a 2-rail cipher has a cycle length of 2. A 3-rail cipher, 4. A 4-rail cipher, 6, and so on. Now, you could work this out by physically drawing out the rails, but there is an equation you can use. Cycles is the number of rails multiplied by 2, and then you subtract 2 from that number. We need to subtract 2 because the top and bottom rails do not repeat themselves within a cycle. Now that we know the length of a cycle, we can work out the width of our puzzle. Count up the number of letters and divide it by the cycle length. And then we need to round down. In my example, we have 21 letters. Now 21 divided by 4 makes 5 complete cycles, and then we have 1 extra letter left over. Once our recipient knows the dimensions of the grid they need to make, they can begin to fill it in. Our first rail needs 6 spaces, 5 complete cycles plus that extra letter. We can write the first 6 letters of our ciphertext into these spaces. The next rail will be 5 times 2, 10 spaces. 2 between each sets of characters on the first line, like so. Our final rail fills in all the remaining letters. The recipient can now read their text from left to right. Hopefully you've got the idea. So now that you know how it works, why don't you give it a try? Can you decode the message shown here? If you want to give it a try, pause now. Did you get it right? Then you're definitely one smart cookie. So as you can see, the rail fence cipher is simple to use, and that is a great strength. But that simplicity is also its greatest weakness from a security perspective. Because there are only a limited number of combinations of different ways that you can set out your grids, that means that if someone knows that you've used this type of cipher, it just takes a few different tries of different combinations, and eventually you will produce a grid that can decode it. Now let's take a look at another method, columnar transposition. Once again, we're going to start by making a grid, and this time we're going to pick a keyword that we're going to use when we're encoding and decoding our message. I'm going to use the word novels. I'm going to write this word out to head up the columns. Then I'm going to look at the letters of my code word and replace it with ascending numbers. E is the first letter alphabetically within my keyword, so that's going to be 1. L is the second, so that would be 2, and so on. Now we have our order, we write out our message from left to right. When we complete one row, we move on to the next. Once we fill our entire grid, we will write out the letters in our first column, then our second, then the third, and so on. Once again, this is actually pretty simple to encode. The question is, how will someone decode it? Well, they'll need to know the keyword. Ideally, you'll have provided this to them separately from sending your coded message, and then that way, no one can intercept it and use it to decode what they found. Start by calculating the number of rows needed. Count the number of letters in your keyword and divide your total characters by that number. Now we draw up our grid with our keyword written at the top. Add extra spaces for each of the extra letters below the column, starting with the leftmost one. Once this has been assembled, we will fill in one column at a time, using the keyword to determine the order of the column. When we reach a column with an extra letter, we will fill that out before moving on to start the next column. When our grid is complete, we can read off our message from left to right. So just like our first example, this is really easy to use, but while it's a little bit more secure than the first example, because the order of the columns will change from message to message, it is still vulnerable to brute force attack if someone has enough time and patience to work out the possibilities. So how would you go about doing that? Look at your coded message and work out all of the possible grid dimensions that could have been used. You then write your ciphertext in columns and try rearranging them randomly to see if you could see anything that looks like it makes some kind of sense. If you don't, move on to the next size grid. There is a way we can make this more secure. We can perform what's called a double transposition. A double transposition is where you take your word, assign a keyword, go through the process once, take the output, pick a different keyword, and run it through a second time. The double transposition method was used by Dutch and French resistance fighters during World War II. It was also used by the German Army and Navy as their emergency backup communication method. The reason that this was picked was it was regarded as being secure enough to pose a challenge to anyone trying to crack it, while at the same time it was easy enough for a field operative to use while under pressure, without making too many mistakes. The double transposition method was regarded as being the most reliable and secure method that an agent could use in the field. It was only surpassed by the Vic code in the 1950s. But that's a story for another time. Join me next time as we enter the communications age. We'll be talking about Morse code, and then we'll be talking about the contribution made by the Navajo code talkers to the war effort in World War II. Thank you.